Quadratic functions and applications are a large part of mathematics and our daily lives. For instance, the force of gravity can be modeled with a quadratic function. Look at the following video. What do you notice about the path of the ball? It changes direction. It was going up and then it went down so that the other boy could catch it. When the ball is thrown, the path forms what is called a parabola. A parabola is a smooth curve which represents a quadratic function. A general quadratic function has the form y equals ax squared plus bx plus c, where a, b, and c are constants, and a is not equal to 0. An example of such a function is y equals 2x squared plus 4x plus 6, where a equals 2, b equals 4, and c equals 6. Other examples of quadratic functions include y equals 3x squared plus 4x minus 6, f of x equals 3x squared minus 2x plus 5, y equals negative x squared plus 7, or simply y equals x squared. For each of these examples, can you tell what the values of a, b, and c are? In the function y equals 3x squared plus 4x minus 6, a equals 3, b equals 4, and c equals negative 6. In the function f of x equals 3x squared minus 2x plus 5, a equals 3, b equals negative 2, and c equals 5. In the function y equals negative x squared plus 7, a equals negative 1, b equals 0, and c equals 7. And finally, in the function y equals x squared, a equals 1, and both b and c are equal to 0. Note that any equation that has 2 as the highest power of x is a quadratic function, and that it is possible for b and c to be equal to 0. Let us look again at the path of the ball in the video. Notice that the path of the ball starts to move back towards the ground after it reaches a particular point. This point is called the turning point. This turning point, because it is the highest point, is called the maximum turning point. Now let us look at the graph representing the quadratic function y equals negative x squared plus 5x plus 6. To draw the graph of this function, we first obtain values for the domain x and substitute them into the equation to find corresponding values for the range y, just as we did when we were plotting linear graphs. Note that the coefficient of x squared is negative 1. Let us look at the table showing the values of the domain and range. That is, the coordinates of the points that will lie on this curve. We take these coordinates and plot them on the graph. Points should form a parabola. We then draw a smooth curve through the plotted points. Since it is a curve, we do not use a ruler because a parabola is a smooth curve and not jointed segments. Do you see that the curve we just drew is similar to the curve formed by the path of the ball? Okay, now let us solve the equation negative x squared plus 5x plus 6 equals 0 by factorization. We multiply the first and last terms, which gives negative 6x squared. We then find two factors of negative 6x squared, which when added together give us positive 5x. These factors are 6x and negative x. We replace the middle term, positive 5x, with these two terms to give us negative x squared plus 6x minus x plus 6 equals 0. Next, we group the terms in twos and factorize each group to give x minus 6 times negative x minus 1 equals 0. So our solutions for x are 6 and negative 1. Now look at the graph and find the point where the curve crosses the x-axis at 6 and negative 1. So we see that the solutions to the quadratic equation are the same as the points where the curve of the same equation crosses the x-axis. This is where y equals 0. Remember the two little boys throwing the ball? The point where the path of the ball changed direction was the turning point. Can you find the turning point on the graph of y equals negative x squared plus 5x plus 6? If we folded the curve so that it maps onto itself, we see that a line which divides the curve into two identical parts is formed, which passes through the turning point. This is the axis of symmetry. The equation of the axis of symmetry can be obtained by reading off the x-coordinate of the line and equating. So, for the function y equals negative x squared plus 5x plus 6, x equals 5 over 2, or 2.5. The turning point of the curve is where the axis of symmetry and the curve intersect. The maximum value of this quadratic function is found by reading off the y value at this intersection. This is 12.25. Therefore, the coordinates of the turning point are 2.5, 12.25. What if the curve had a minimum turning point instead of a maximum turning point? Let us look at the graph of the function y equals x squared minus x minus 6. Just as before, we obtain values for the domain x and calculate corresponding values for the range y. Let us look at the table showing the domain and range. Now we plot the points and draw a smooth curve through them. The curve has a minimum turning point this time. What would be its axis of symmetry? X equals 1/2. The minimum value would be negative 6.25. So the coordinates of the minimum turning point are 1/2, negative 6.25. Okay, now let us solve the equation x squared minus x minus 6 equals 0 by factorization. We multiply the first and last terms, which gives negative 6x squared. We then find two factors of negative 6x squared, which when added together give us negative x. These factors are negative 3x and 2x. We replace the middle term x with these two terms to give us x squared minus 3x plus 2x minus 6 equals 0. Next, we group the terms in twos and factorize each group to give x minus 3 times x plus 2 equals 0. So our solutions for x are 3 and negative 2. These points are the points of intersection of the curve and the x-axis. It is important to note that when drawing graphs of quadratic functions, if the coefficient of x squared is positive, then the graph has a minimum point. And likewise, if the coefficient is negative, the graph has a maximum point.